and difficult things in noise. First up, we have Andrew talking about optimal 2-qubit circuits.
So my name is Andrew. I recently graduated from the University of Maryland at Quicks, and now I actually work for a consulting firm in DC called Booz Allen Hamilton, but I still do quantum research, so still doing the same thing I basically did in grad school. And today I'm going to talk to you about optimal 2-qubit circuits for universal fault-tolerant quantum computation, and this is work I did with my collaborators, Neil Ross, who was supposed to be here today, but his flight unfortunately got canceled, and my former advisor, Jake Taylor. And I should note that this paper went on the archive literally Friday, so check it out.
Is that the same Jake Taylor who works in the government?
Yeah, he works for NIST and also, I can't remember the OST or something, yeah. Okay, so you've been hearing a lot today about quantum compiling, and I'm going to speak to you about quantum compiling within the framework of universal fault-tolerant quantum computation. And so in order to do that, I'll sort of like give my spin on the problem statement, if you will, which is kind of condensed from a variety of sources. But basically the goal is to find, given a target unitary, find some gate sequence, which over your gate set exactly or approximately implements the unitary in as low cost of a circuit as you possibly can for a given cost metric. And so there's kind of a lot to unpack here, so I'll try and do it line by line. So given a target unitary, find a gate sequence. Basically, the unitaries we're talking about synthesizing here are typically few qubit unitaries. And the reason for that is even specifying like 10,000 qubit unitary is just, it's not really like a feasible thing unless you can write it in some very special form. And also quantum algorithms give us unitaries typically packaged into small, like few qubit circuits. And so by find, I mean it needs to be efficiently computable as well. So over your gate set, what do the unitaries in your fault-tolerant gate set actually look like? You need to know like whether some unitary handed to you is in some gate set or not. Exactly or approximately within error epsilon implementing. This means, do I have an algorithm for exact synthesis? When I know a circuit is in my gate set, can I synthesize that circuit? Likewise, when I know the circuit is not in my gate set, can I synthesize that circuit? And then as low cost a circuit as possible for a given cost metric. So we need to think a little bit about what the sort of cost metric that makes sense for universal fault-tolerant quantum computation. And so because we're fault-tolerant, typically we're assuming that we're using quantum error correction. We're assuming that we typically have transversal Clifford gates. So Clifford gates are kind of cheap in some sense. And then using magic state distillation, where magic state distillation is really the thing that is difficult to do. And so because that is the case, typically the T count is used as a cost metric. In my case, I'll be talking a little bit more generally about like the non-Clifford count, where these non-Cliffords are specifically those that can be implemented using magic state distillation techniques. Okay, so building a good compiler for a universal fault-tolerant gate set. So for any gate set, you have kind of three ingredients. You have some exact characterization of unitaries over that gate set. Then you want some exact synthesis algorithm, so basically a way to go from your gate set to some hopefully optimal circuit and T count. And then also some inexact synthesis algorithm, basically some way to round a generic unitary into your gate set unitaries. And so for the single qubit Clifford and T gate set, this is already accomplished. The Matsumoto-Amano normal form in combination with the characterization by Vadim Klushnikov and collaborators, as well as Neil Ross and Peter Selinger's rounding algorithm. But as far as going beyond single qubit Clifford and T, the results have been not as forthcoming. So we have kind of bits and pieces here and there. For example, we have a full characterization of Clifford and T unitaries on arbitrarily sized circuits. There's also like plenty of work in like ZX stuff, which is kind of different from what we're doing here, but tries to answer some similar questions. But even just doing 2-qubit circuits is difficult. And so what do I mean by that? So we don't even have like an optimal synthesis algorithm for like 2-qubit Clifford and T. And the reason is that group has relations. So this is not just some arbitrary circuit. This is like a defining relation for the 2-qubit Clifford and T group. There's like 22 T gates in here. I have no idea how to use this to optimize the circuit. It's difficult. And so our idea was to, rather than looking at Clifford and T directly, use some subset of Clifford and T, the Clifford and control phase gate set, which is also called the super Gaussian Clifford and T gate set. You can read a little bit more about this gate set in this paper where we actually characterize unitaries. But this gate set has the phases omega, which is like an eighth root of unity. You have your standard set of single qubit Cliffords. You have your 2-qubit Clifford, control Z or control X, whatever you want. And then you have this CS gate, controlled S gate. And because it's a controlled Clifford and explicitly not a controlled Pauli, we know that it's a non-Clifford gate. And in particular, it is one that is, you can use magic state distillation to implement. OK, so in order to actually make some progress on this problem, we're going to first define a channel representation in analog with past work. And basically, we want to define this set of operators, which is this CS gate conjugated by every single Clifford in the 2-qubit Clifford group. So there's 92,160 of these. So nominally, this is a big set. But actually, it reduces down quite a bit to just 180 elements. And you can specify these using 2 commuting Hermitian Paulis P and Q. That's why I wrote this way. And then using this new definition, we can come up with some pretty straightforward relations for this gate set. So there's this relation for pushing Cliffords through any of these RPQ operators at the cost of just conjugating your Paulis here. We have that one of these operators squared is in Clifford. This is true because control phase squared is control Z, which is in Clifford. And then you have this set of 3 relations, which basically define symmetries on these, that occur with these Pauli matrices. And so these actually reduce the set even further to sort of 15 canonical RPQ operators. We'll call this set S. And then finally, we have one relation here, which is slightly non-trivial because it's not just relating, basically 1 to 1 or 2 to 0 or anything. It's like 2 to 2. And this is going to come back a little bit later. I'll talk about it a little later. So in order to rewrite a circuit, we can start from the general circuit of Cliffords with interspersed control phase gates, so n of them. Replace each of these CS gates by RZ1, Z2. These are exactly equivalent to one another based off of my definition. And then you apply relations from left to right. So again, we can always push Cliffords to the right. So basically, we will push Cliffords to the right, and then if we get a RPQ operator that's not in our canonical set, we use one of those relations to turn it into one. And you end up with something that looks like this. Basically, just a series of RPQ operators followed by some final Clifford. And explicitly, this n prime, so that's the number of these, can only be less than or equal to n. And that's because of that squaring relation where 2 of these RPQ operators squared is in Clifford. And so then this still begs the question. So this is we are handed a circuit and trying to optimize it. But how do we find such a circuit just given a unitary, where we don't know the internal guts of it? And furthermore, is that circuit optimal? And to do that, we're going to use this exceptional isomorphism between SU4 and spin 6 to come up with a simpler representation. So this isomorphism is defined using the wedge product. It's not that important that you understand this, but I'll just do it for posterity's sake. So this wedge product is antisymmetric. It's bilinear. It's also associative, but we won't use that because we're just doing wedge products like this. And you compute inner products between the wedge product of two vectors as this. And then, so we need to define how operators act in SU4 and how that corresponds to how operators act in this spin 6 representation. And so they act via this relationship here. So basically your SU4 operator U here, you act it on the two vectors you're taking a wedge product of, and that defines basically how your spin 6 representation looks. And then we simply define some 6-component basis using this wedge product. It's not really important what the form of these things is, but basically you use all of these relations and churn the crank. Everything you need is up there to compute matrices in this spin 6 representation. Okay, so when we actually look at the spin 6 representation of our generators, it turns out that the Cliffords are all 23,040 generalized permutations of spin 6. Now this should give you some pause because I told you there were 92,160 earlier, so we're off by a factor of 4. But it turns out this factor of 4 basically corresponds to 2 factors of 2 that come from ignoring phases, roughly speaking. Now, operators from this set S pretty much all look like this. They all look like this, essentially. And so these little dots here, I just wrote those instead of zeros to make it a little clearer. But they all look like 1 over root 2 times these sort of like blocks that kind of look like Hadamards. And then, so if we were to take a product of Cliffords and anything in this set here, they belong to a group G, which is basically special orthogonal operators, which can be written as 1 over root 2 to the k times some matrix of integers m. And so we want sort of a more convenient method for analyzing matrices over this group. And so rather than look at the matrix just as it is, we're going to define some residue map which looks at elements of G. And basically for this k being as small as possible, so the smallest possible integer, which is valid, we look at this matrix M mod 2, whether the entries are even or odd. And so if you do that for any k value greater than 1, in order to enforce orthogonality, your only possible options are matrices that look like this. Basically the one I showed you earlier, the one I showed you earlier with zeros and ones switched, and then this one with like a block of 4 by 4 odd entries. And so obviously this is not all of them. This is just up to a permutation of rows and columns. And what we sort of identify here right away is that rows come in sort of these pairs, or sometimes like a pair of 4, basically patterns in the matrices. And these patterns are just partitions of the set 1 to 6. So like the row pattern here would be like 1, 2, 3, 4, 5, 6. Same with this one. And if you try and count out what all the possible patterns of 2 by 2 by 2 and 2 by 4 partitions are, you'll see that there are 15 of both. And so this 15 should sort of sound familiar from something I said earlier in the talk. And so we can use this sort of observation to come up with a synthesis algorithm where we recognize that the row patterns of these elements of G are always coarser than at least one of these generators in our set S. And by coarser, I basically mean this set is coarser than this one because this one is somehow a finer partition of this other set here. So this allows us to basically use something that people in the field like to call constrained Gaussian elimination in order to reduce the denominator exponent, basically reduce that k 1 by 1 until we reach something with a denominator exponent of 0. And so given that this first bullet is the case, we can basically generate a key for every partition that is possible. And so we actually have some freedom when you have partitions that are like 2 by 4. And in particular, you have 3 choices for those. And that actually comes back to that relationship, that relation I showed you earlier that I said was a little bit more complex. It's basically enforcing you to pick a choice if you want a unique synthesis algorithm. And then, so synthesis is relatively straightforward once you've done all these things. You basically reduce the denominator exponent 1 by 1 to 0 using these generators. You return to the identity by basically multiplying by a Clifford, and then you just invert that whole sequence, and that is exactly the operator you started with. And so to give you an example of a synthesized circuit, here's just some random circuit over this gate set. When you do the isomorphism, you see you get some matrix here. The denominator exponent is 14. We spit out some big circuit in terms of our generators. I use some slightly altered set of generators here to make it a little cleaner. And then we can check that in fact that indeed these two things are equal. But one observation here is that we require at least k CS gates to achieve this denominator exponent of 14, because that's the only gate that comes with like a factor of 1 over root 2. And the spit out operator here contains exactly k CS gates. And so that implies that we actually have an optimal normal form over this gate set. So in conclusion, the results we derived here are that we have this synthesis algorithm, which is linear in the number of gates. I'll actually end up posting some code to GitHub so you can check that out. Every normal form here is unique and optimal, where the normal form is simply the output of the synthesis algorithm, essentially. We actually go on to describe the structure of these normal forms. If you want to dig into this, you can look at the paper. It's a little more involved. And then finally, using some volume counting argument, you can show that you need 5 log 2 1 over epsilon CS gates to epsilon approximate any unitary, at least 5 log 2. And so with that, I'd like to thank my 2 collaborators and open it up to any questions. Yep.
Just a clarification. Your last slide, you said the algorithm was order n. What is n?
N is the number of gates. So if you're starting from like a sequence of n gates in your circuit, like you're just handed like a circuit, it will take order n time. And if you're just given a unitary, n is the number of syllables in your circuit. So basically the number of or the denominator exponent when you look in the transform basis. Yep.
Can you just say a little bit about the applications of this?
Yeah, so the idea in general, I think, is take fault-tolerant compilers on few qubit circuits and apply them to basically the submatrices of, Hamiltonian simulation is something where typically the circuits you're talking about only act on a few qubits at any given time. And so the idea is, rather than having to break those few qubit unitaries down into just single qubit unitaries and controlled operations, just do the whole thing at once, basically. And of course, that requires some like rounding algorithm, which is something I've worked on like a little bit here. But yeah, so basically, it's like we're basically just brute forcing truth tables in some sense, like, what is the optimal circuit for like a 3-bit circuit or something is easy to brute force. Doing it on 3 qubits is not so easy to do. There's like diminishing returns here, but eventually, there's going to be some meat in the middle where you're like, okay, that's good enough, and then probably use those as subroutines.
Maybe one more.
So what is the gate complexity you consider about if you want to use standard Clifford plus T to implement your control phase gate?
So it takes exactly 3 T gates to implement 1 CS gate.
Each?
Each. It's not true that you couldn't find a shorter Clifford and T circuit that implements a Clifford and CS circuit, but it's just a constant factor.
Oh, so which means that your result just gives up to constant 3 the optimal decomposition of Clifford plus T for any 2-qubit gate? Can I regard it that way?
That's right. But the thing is, like, even with just single qubit, so we have a single qubit Clifford and T synthesis algorithm.
Yeah.
And that is, strictly better than the performance of this for just like single qubit circuits, for example.
Yeah, but your result is for 2-qubit, but not 1-qubit.
That's right. So it is for 2 qubits and like generic 2-qubit circuits, but like, I don't know. It's just I would not necessarily claim that this algorithm is going to like replace the Clifford and T one so much as the techniques used in it will probably be used to further techniques for larger Clifford and T circuits, for example.
I see. Because as far as I know, that any 2-qubit gate can be implemented using 3 CNOR gate plus some 1-qubit gate, so you can then run a standard wave. So
exactly.
Can you compare these two methods?
Yeah. So Clifford, if you used Clifford and T to do that versus this, single qubit Clifford and T synthesis algorithm is strictly better than the performance of this. So again, it's like, you're looking more so to use these techniques for Clifford and T, for example.
Great. Can the next speaker come up? Thank you, Andrew. Oh, your mic as well.
Yes.
I'll turn this on. Can you say something to make sure that it works?
Hello?
Okay, good. I think so. And then just slip that into a pocket somewhere convenient. Okay.
Great. So our next speaker is Yu Zhang, who'll be talking about context-sensitive qubit